Welcome back to AI Codecast. Today, we're going to dive into a classic coding challenge, finding K-Diff pairs in an array.
Yeah, it's like we're on a treasure hunt for numbers, but with specific rules.
Exactly. So imagine you have a list of numbers, right?
Right.
And the challenge is to find all the pairs that are exactly K units apart.
It's a problem that you see all over in programming, like analyzing data trends or optimizing search algorithms even.
Okay, so let's take an example. Let's say our list of numbers is like 3, 1, 4, 1, 5, and K is 2. What pairs would fit the bill?
Okay, let's see. We'd have 1, 3, and 3, 5 because their difference is exactly 2, right?
Exactly. But there's a catch. We only care about unique pairs.
Oh, right.
So even though the number 1 appears twice,
Mm-hmm.
1, 3 is only counted once.
It's like finding matching socks. You only need one pair, not two of the same left sock. Haha.
I love that analogy. Now let's start with the simplest approach, brute force.
Yeah.
It's not always the most elegant, but it helps us grasp the problem. So how would we go about this?
Well, brute force is kind of like checking every single possibility. So we'd compare each number in the array to every other number, and we'd calculate their difference and see if it matches our K value.
So we're essentially going through every combination one by one. That doesn't sound very efficient.
Yeah, you're right. It works for smallest, but imagine doing this for a data set with like millions of entries.
Oh, wow.
It would take forever. And that's where the concept of time complexity comes in.
Time complexity. That sounds a little intimidating.
Don't worry, it's not that scary. Think of it like this. If brute force is like walking to the store, right, a more efficient algorithm might be biking, and the most efficient one might be like teleporting there instantly.
Okay, I'm starting to get the picture.
Yeah.
So how would we measure the walking speed of our brute force approach?
In this case, we'd say it has a time complexity of O entries on, which basically means that the time it takes grows exponentially as the number of elements in our array, which is increases. Not ideal for massive data sets.
So brute force is like our trusty but slow old car. Gets us there, but maybe not the best choice for a cross-country road trip.
Exactly. So how could we speed things up? Imagine we already sorted our array from smallest to largest. Would that help us find those K-Diff pairs faster?
A sorted array. Let me think. If the numbers are in order, we wouldn't have to jump back and forth so much, right? Maybe we could strategically eliminate some comparisons. I'm thinking we need a smarter way to navigate through the array.
You're on the right track. What if instead of checking every single combination, we could use 2 pointers to guide our search? Kind of like 2 fingers scanning through the list?
Okay, 2 pointers, one at the beginning and one at the end of the array.
Precisely. We compare the numbers they point to, and based on their difference, we move one of the pointers, cleverly narrowing down our search.
Now that sounds way more efficient than blindly comparing everything. Let's dive deeper into this 2-pointer magic in the next part. But before we move on, I want to throw this question out to our listeners. What are some real-world situations where finding K-Diff pairs could be useful? Share your thoughts in the comments, and we'll explore some possibilities in the next part. Welcome back to AI Codecast. We left off talking about using 2 pointers to find K-Diff pairs more efficiently. I'm excited to see how this works.
Yeah, it's a really cool strategy that you'll see a lot in algorithms. The key is that we're taking advantage of the fact that our array is sorted.
Right, so we have our 2 pointers, one at the beginning and one at the end of our sorted list. What's next?
So we compare the values that those pointers are pointing to. We can call them left and right to make it easier to talk about.
Okay, left and right. Got it. So we calculate the difference between those 2 values, and then...
This is where the cleverness comes in. If the difference is smaller than our target K, we need to increase it. How do you think we can do that?
Well, if the difference is too small, it means our right pointer needs to move towards a bigger number, right?
Exactly. We just slide the right pointer 1 step to the right, and that increases the difference.
Okay, that makes sense. What if the difference is bigger than K, though?
Then we do the opposite. We move our left pointer 1 step to the right towards a larger number, which decreases the difference.
So it's like we're constantly adjusting our aim, bringing those pointers closer or further apart until we hit that target difference of K.
Exactly. Now, what happens if the difference is exactly K?
That's got to be a bingo, right? We found a K-Diff pair.
You got it. We add that pair to our collection. But remember our no double dipping rule. What do we need to do before we keep going with our pointers?
Oh, right. We need to make sure that both of our pointers end up on unique numbers before we calculate the next difference. We don't want to count the same pair twice.
Exactly. So we might have to move one of the pointers a few steps until it lands on a new distinct number. This makes sure that we're only counting each unique pair once.
So we're not just randomly checking every combination anymore. We're being strategic with our pointers and zeroing in on the pairs we need. That sounds a lot faster.
It is. This two-pointer technique brings the time complexity down to ON login, which is a big improvement over the ON of brute force, especially when you have a lot of numbers.
O and log n. I'm guessing that has something to do with the sorting step we did earlier.
You're right, the two-pointer part is really efficient, but we do have that initial cost of sorting the array.
It's a trade-off then. We spend a little time sorting up front, but then we gain a lot of speed when we're finding our pairs.
Exactly. And a lot of times that trade-off is worth it, especially when you're working with huge data sets.
This has been a fantastic explanation of the two-pointer technique. I can definitely see how this could really change the game when it comes to optimizing code.
It's all about knowing the strengths and weaknesses of each approach. Sometimes the simplest solution is the best, but in cases like this, a little extra cleverness can make a huge difference.
I totally agree. Now, before we move on, I want to pose a little thought experiment to our listeners. What if instead of K-Diff pairs, we were looking for triplets that added up to a specific sum? Do you think we could use this two-pointer technique for that too? Think about it while we dive into an even more efficient method using the power of hash maps in the next part. Welcome back to AI Codecast. We've talked about brute force and the two-pointer technique for finding those K-Diff pairs. And now it's time for the secret weapon hash maps.
Yeah, they can really be a lifesaver when it comes to speed and efficiency in programming.
Okay, and I'm intrigued. How do hash maps help us solve this problem?
So think of a hash map like a really organized toolbox where every tool has its own special spot.
Okay.
And in this case, our tools are the numbers from our array, and the spots are unique keys.
So it's not just throwing all the numbers into a random bucket. We're putting them in a very specific, easy-to-find place.
Exactly. And the great thing about this is that we can instantly check if a number is in our hash map without having to search through the whole array.
That makes sense.
Yeah.
So how does this help us find K-Diff pairs?
Well, for each number in our array, we figure out its complement. Remember how we were talking about needing two numbers that are k units apart? The complement is just the other number that would make a K-Diff pair.
Let me see if I get it. So if our k is 2 and our current number is 3, its complement would be 5 because 3 plus 2 equals 5.
You got it. And it could also be 1 because 3 minus 2 equals 1. We got to consider both possibilities.
Right. So we use the hash map to quickly check if either of those complements is already in there.
Exactly. If we find a complement, we know we've got a K-Diff pair. And since hash maps are so fast at lookups, this whole thing becomes super efficient.
Wow. Hash maps sound like they were made for this kind of problem. What kind of time complexity are we talking about here?
On average, it's O-may, which means the time it takes basically grows at the same rate as the size of the array. It's the most efficient way we've talked about so far.
So if brute force is walking and two pointers is biking, then hash maps are like taking a bullet train.
Haha, I like that analogy. But just like with any tool, there are trade-offs with hash maps.
Oh, what kind of trade-off?
Well, they do use extra memory to store the hash map itself. So if you're working with a truly massive amount of data, that memory usage could become a problem.
So it's not always a clear winner. We have to think about how much data we have and what resources are available.
You got it. If memory isn't an issue and speed is super important, then hash maps are the way to go. But if memory is limited, then the two-pointer method might be a better choice.
This has been such a cool deep dive into finding K-Diff pairs. We started with the simple but slow brute force approach, then we moved on to the elegant two-pointer technique, and finally we got to experience the power of hash maps for that maximum efficiency.
Yeah, it's a great example of how understanding different algorithms can really help you write smarter and more efficient code. There's almost always more than one way to solve a problem, and the best solution depends on the situation.
Absolutely. And to all of our listeners out there, we encourage you to try these techniques out yourself. Implement them in your favorite programming language and maybe even come up with your own twists on them. Who knows, you might discover an even better way to find those K-Diff pairs. Thanks for joining us on AI Codecast, and until next time, happy coding.